Okay. So we're asked to graph y equals 2x minus 3. Here's something you've learned, but I'm going to reiterate. It's impossible to get this value here to equal 0. You can't have it. Remember, it never gets there. It hits an asymptote. Right? It can't equal 0. But does it come close to 0? Remember we got really small decimal 0, but not quite 0? So if you use your imagination, you could imagine that circled green bit could become 0 if x was the right value. If it comes so close to 0, like 0.00000000000. So what I want you to do is when you get these equations that have something added or subtracted to it, imagine this is 0. Then, super easy, the asymptote is right here. There you go. There's your asymptote. So now you can go to your graph where minus 3 is. Draw an asymptote. Huh? So that was easy. It's this number hanging out back here. Next step, you ask yourself this question. This is base 2. So is this growth or a decay type? Look at the base. The base greater than 1? Yeah, it's true. If it wasn't, it would be between like 0 and 1, and it would be decay. So this is growth. And growth, we know, looks something like this. So that's what we're aiming for, that shape. So that's so far, that's a couple checks. Last thing to do. Okay. We generally know, I mean, I'll just quickly, it's got to look something like this. Don't draw that yet. It's got to look something like that. We need one more point. Okay? Yeah, Brooke?
How do you know it was a growth?
Growth property is such that this this value here, the 2, since b equals 2 and b is greater than 1, we have growth. As soon as b is greater than 1, it's growth. Between 0 and 1 is decay. Okay? Essentially, if you see a fraction in here that's less than 1 or a decimal number that's less than 1, that's positive, you would have decay. We have growth. We have one more thing to do. It's really easy. We're going to use the y-intercept. The y-intercept, by definition, happens when x equals 0. So I'm going to put x equals 0 in this equation. Two to the 0, anything to the 0, 1. Subtract 3. Okay, so you've got a nice y-intercept point, and it's written this way. Let's put that point on our graph. Right here. Okay? Roll all this information up. We know its growth has to have this shape. We know where it crosses y. It crosses y at the y-intercept at minus 2. Okay? And we can sketch. This would be considered a sketch. Okay? And you've got your basis now. With the data table, which we talked about the last couple days, you could get more precise. Wholly could get more precise. but this is a great way to sketch it. Pretty easy. You know right away where the asymptote is. You look at your base, see if it's growth or decay. Find the y-intercept, put the information together, and sketch your graph. Yeah. Please?
The y values when you're doing the r dot brackets, that it's not less than 0 but less than negative, greater than negative 3.
Yeah, so we'll update our domain and range. When you said R, you meant range, I believe. So this thing's domain. Okay? It's going to use all the x values because the graph continues this way in negative x and it continues to the right with positive x. Range is going to use real numbers as well, but the difference is this time it's always going to be greater than what? Like the asymptote blocks you at -3, right? You can't cross -3. It'll never come down here. So it's always got to be greater than -3. This thing is always increasing. Always. Look left to right. You read it left to right. You follow the y values as you go left to right. And if you can imagine every y value, it keeps increasing, increasing, increasing. Okay? Okay, so that's a good way to sketch it. Also acceptable. Okay, so the other part of the homework, and I'm just going to take every question up because I want to show you a different way of doing it. Who's heard of a spreadsheet? What's a spreadsheet? Microsoft Excel, OpenWriter has a spreadsheet too. Okay. You were asked to do these questions in your book, page 324, 5, 7, 8, 9, 10. I'm going to take them up right now. It'll probably be done in about 3 to 4 minutes because I'm going to show you my spreadsheet method I used for it, which is the same as paper pencil, but a bit different. So hopefully you've had a chance to read these. They're application questions, and we're going to take them up. All right, here's number 5. So for those of you who've actually done the question, will recognize that the data they gave you in number 5 was the time versus share. Okay, and when they posed the question, they said times x shares your y value. Okay, so when you take a look at these data points, is it logarithmic? Is it exponential? Is it trigonometric? Is it quadratic? Is it linear? What kind of equation? And we have methods to do that. You take the ratio of all these numbers, and it came out as 1.01. And we learned that when ratio is the same, it's exponential. The first differences come close to being the same, so do the second differences, but I think the ratios are better. And how am I doing this? You would do 20.52 minus 20.32, you write the answer there. 20.52 minus 20.32, write the first difference answer there. How do I get the second difference? This subtract that goes here. This subtract that goes here. Ratios just divide these two, they go there. Divide those two, it goes there. Divide those two, it goes there. It's a ratio. So I found that ratio wins, but when I graphed it, it looks linear. And that's why the book told you it's linear, maybe it's quadratic, maybe it's exponential, maybe. Because when you graph it, it kind of looks linear. It could almost be considered quadratic too, if we extend the graph, but to me it's exponential. It's number 5. Okay? You're also asked to do number 7. And in number 7, there was a situation where time for x was looked at against pressure. And I did my ratio first difference and second difference. I graphed it as well, and this is screaming exponential. Look at the graph. It shoots down really fast. The ratio is all worked out. That was exponential. Okay? When I did number 8, it was the same thing. Same approach. You're looking at radius, you're painting something versus its cost to paint. And when I did the ratio, they didn't equal out. The first differences didn't equal out. So I did the second differences, and finally they were all the same, basically. The real world's kind of messy. It wasn't exactly the same. When I graphed it, okay, I put these 4 points down. 1, 2, 3, 4. And I extended my symmetrical quadratic, because the quadratic is symmetrical. And it looks pretty quadratic to me. Yeah?
Are you supposed to graph it until we understand?
You don't have to graph it. I just did so I could see it. It didn't ask you to do that in the question. You could actually answer every single one of these questions just with the first difference, second difference in ratios. Graph helps you see it. Number 9, it was the same story. Okay, and that's how you do it. You do it with ratios. When I graphed it, the loudness of sound, okay, when someone speaks, it's a sound wave. It pushes the air. And pushing the air, when you push on something, it's pressure. You exert pressure. So when I speak, sound is sound waves. They hit the air in the room, and that's what you're hearing. That's loudness. Okay, that's like the loudness goes out, it creates pressure, and you're hearing sound. This was one where 80 units of loudness creates that much pressure. That's like how I'm talking right now. Go to like a plant where they make widgets and gadgets and cars and whatever. It's about 100. Okay. Go to a concert, screamo metal, okay, or hard rock and roll, really heavy. You're looking at about your front row, 120. You're going to blow your hearing. If you ever see a sign 120 dB or louder, run. You'll be deaf. It's true. About 130, you can pop your eardrums. It's measured in dB, decibels. Okay. Number 10 was the same story, essentially. It worked out to be first differences were the same. And look at that. First differences, it's a line. It's linear. Okay. Were there any specific questions with any of these? So totally questions like this. Graphing these, both methods, table of values, using the method I showed you today, using first differences and that, totally what you can expect probably next Tuesday or Wednesday on your test. Okay? Questions? No? Okay. Maybe? Okay. We're changing gears then. We're moving in today's lesson, which is going to be maybe 40 minutes. Depends on your questions. And then tomorrow's a work period on it. And this is where we've got the basics, right? We've got exponentials, all the laws, we can do the algebra, you've been shown how to graph them, and now we can move in applications. But I'll tell you this, these applications won't involve graphing. Okay? Won't involve much graphing. Mostly little word problems. You'll see how it comes together. So, I have a handout for you. And you're about to get it. And it looks something like this. And as I said, this is one of those lessons where you want to hear it. You want to participate because it's something that builds. We're doing a discovery lesson. I'm going to show you basic stuff and build it up into one formula that takes care of everything. Okay? And these little situations will apply to various people in various ways at different times in their lives. And there's no homework. So we'll use this note today and tomorrow, and we'll give you a full work period tomorrow. This is the last part of this unit. Part 1 was all the algebra, the rules. Part 2 was the graphing. Part 3 of this unit is these applications. Okay, so Andy, you want to track that window? Make sure it's open. Yeah, get it open, please. It's too warm. Even only if you can open the back window a bit, that'd be awesome, please. Okay, it's a pretty easy lesson. It's just it keeps building. Yeah. Okay, sorry guys. You too, Samantha? Yeah. Okay. Okay, word of caution. I'm going to write on the note. It looks just like your note you have. And then I'm going to erase a lot. So if you're using pen, you're going to have to, you don't want to be scratching it out. Maybe just listen and wait. It's very brief things we need to write. It's not much. There's not a lot of text. It's mostly just equations. So don't write Don't write every single thing I write down. Okay, I'll be very clear. Okay, we have to figure out a way to use exponentials to do applications, and when it comes to exponentials, they're either growth or decay. They're either growth or decay. We're going to skip this and come back to this at the end, because we're going to discover the general formula for growth and decay applications today. We're going to show you some situations and discover. So skip down where it says number 1. Okay? So all little situations that will affect you in life could easily come up. Mostly. Okay, here we go. So we're going to write an equation. So we need an equal sign, we're going to need usually a y value and an x value, and they're exponential. Allowance. If you had to pick a real variable that works good for allowance, y is boring, y and x, they just belong in the math world. Let's use some real world variables. What would be a good letter for allowance? A. Okay, let's go with A. So far, so good. We got an equation going, okay? So you can write A down and then erase that. All right. You're going to start, first year, you're going to get a $5 allowance. So you're going to write 5 down, and I won't be erasing that. That's the first year. How much are you getting in the second year, Jade? If it doubles, so how do we get it to double? We'd have to multiply it by 2. Okay? So the second year, you get 10. The third year, it has to double again. I'm going to write in blue. Don't write this down, but just watch. The third year, it doubles again. So, I mean, that's the same thing as multiplying by 2, right? First year, you get 5. And then you double it, so you have times 2. You double it again, you have times 2. The next year, again, you'll double it again. And then you'll double it again. And double it again. So, how many times do I write 2 down? Well, I don't know. I don't know how many years I'm going to do this for. So is there a better way? Yeah. Okay. Why don't we use an exponent? I agree. So instead of writing 2 down a bunch of times, it's basically 2 times 2 times 2 times 2, as many times as I want to do, as many years as I'm going to do this for. We'll do it over years. What would be a good exponent? X is okay. X is like math world, kind of boring. This is happening in the real world per year. Yeah. Why? Y is no good. No.
A year.
For years, what's a good one now? What? No, B is no good. Come on, years is a
L.
L. Physics people, what do you measure years with?
365.
Time. So T makes the most sense. Okay? There you go. You've written in a little equation for that situation. Okay? Your amount starts at $5. Depending on how many years you end up picking to check this for, I didn't tell you what T is. I could say T is 10 years. It's checked in 10 years of our ounces. So I don't know how many years, but I just know it's going to double each year, so I'm going to put T. Just a variable, T for time. Okay, so same idea here. Your $7 allowance. Start with $7. Your amount starts at $7. And the next year, it's going to go up by 1.5. That's your new allowance the next year. The year after that, again, when I write in blue, I'm usually going to erase it. It's going to go up again. And then again. And then again. And then Nicole, instead of writing 1.5, a while ago you said we could do something. Do you have any recommendations again this time?
Same thing.
Same thing. So instead of writing 1.5 a bunch of times, let's use T for the amount of years we're going to do this. T is like the number of years. Yeah.
You're saying that when you said before you didn't want us using decimals, so if we were going to solve that, would we have to do 3/2
No.
T? Or we're allowed to use them today?
When it's presented as fractions and it comes in as fractions, leave it as a fraction. But when you can bring it in right away as a decimal, like on the word problem, go ahead. Yeah. Especially if it's a clean decimal. This is a terminating decimal. It's a nice rational number. It works really well. Okay. Okay, not bad. Now I need to check something. This is not in your note. But this is one of those things that you should know how to do or you're going to have trouble. Who can tell me how to write 200% as a decimal? Let's write 200%, Nicole, as a decimal.
2.0.
No. Let's write 50% as a decimal. Help me out. How do we write, Matt?
It's 0.5.
0.5. Okay. What about 2.5%? How do we write? These are basics. These are basics you should have mastered in grade 8, 9, 10. So I'm going over them just to make sure. How do you change 2.5% into a decimal? Let's look at how we did this. We had 200%. There's sort of like a decimal here, and I had to move it over twice. Here, it's like there's a decimal here, and I moved it over twice. So here, I need to move it over twice. And it's 0.025. Okay, this is important. You have to be able to do this right away. Just quickly change percents into decimals. Another important thing is the following. When you start something in life, when you start an adventure, when you start a project, when you start to do something and you're ready to get going, at that point in time, you always start with what you currently have is 100%. Okay? So if you're going to do something that causes this to grow by 50%, you're going to grow perhaps by 50%. Well, if you're going to grow by 50%, you would add 50. And you have 150%, which you could then change to a decimal as 1.5. Okay? That's growing. We always start with 100%. Growing, I added 50%. Well, what about this? We can figure this out. If you always start with 100%, and something decreases by 40%, how do I write that as a decimal? Like final answer. If this decreases by 40%, you're left, your decay down 40%. Yeah, go ahead, Brandon.
60%.
And the way he did that, which is correct, when you're decreasing, you're subtracting away what you're decreasing. You're left with 60%. Okay? And that's 0.6. So that's a little aside. You need to be able to do that pretty quick. Okay, I'll do one more decreasing. If we are decreasing by 5%. What's the decimal already? It's not this. The final answer is not this. So rethink, that's what you're going to say. We have to decrease. We start at 100. We decrease by 2.5. Brandon and I have already checked with you, so thank you. We started out at 100. Everything starts out at 100. And then you lose 2.5%. Where are we at? Haley, you got it?
No.
Haley, take away 2 from 100. What do you have? Take 2 from 100. What are you left with?
Is it 97.5?
It is 97.5. So it's 97.5%. Okay? Which you then write as a decimal. Move it twice. And there you go. Okay? Important to know. So back to the lesson, we need to know these things. Okay, you invest $100. So investments, I think maybe the letter I could be good. Or when you invest, usually you want to get that return. You could use R, but I'll use I. I'm just showing you what goes through my head and probably goes through your head. And just commit to something. I for investment. So we start with 100. Now, remember I said at the start, you always have 100%. When you start some kind of task in these applications, you got 100%. How much are we either gaining or losing where are we going to? Who can tell me where we're going to arrive based on it saying investing 100% at 2% per year? How much more are we going to get the first year? We start at 100, and it says something about at 2% per year. What do you think the new...
You're getting $2 each year.
You are, but if we want to think about it, we start at 100%, but we add 2%. So that's 102%, which is really 1.02. Okay? So 1.02 is the key thing to find there. Okay? And here's how this works. You're going to multiply the amount you started with by a factor, by an amount of 1.02. Matt, when you said $2, what's 100 times 0.02? 2. So if you just do the full amount, 100 times 1.102, you'll get 102 right away. It's faster, right?
Yeah.
That's why we do it that way. That's the first year. If we want to do it another year, if we want to do it again, we're going to get some new amount. When we get that new amount, the next year, again, it's going to be multiplied by 1.02. And then again the next year. So do we see the same pattern Nicole pointed out earlier? We keep multiplying the original amount by the same multiplication factor, 1.02. So instead of writing that out a bunch of times, let's just use a variable. How about t for time? So if I said to Matt, I want to know if I put $100 away at 2% per year, in 10 years, how much will I have? Where are you going to put this 10 in the equation? Where the t is. Okay? And you could figure out in $100 going in at 1.02% per year, how much that is. You could. I'm not asking you to do that yet, but that's what's coming. Okay, here's this one now. A car, you buy it for $25,000, and it's going to depreciate. What in the world does that mean? What happens when you depreciate? Yeah, Matt.
That means you're losing 30% a year, so what should you buy?
So you're losing 30% per year. So remember we start at 100%. We lose 30%. So we're left with 70%. And 70% is 0.7. Okay. So that's like converting our, essentially what's a multiplication factor into a decimal. That's the steps. And then here's how you write the equation. We'll go with A amount. The amount we'll have for that car to be worth after so many years. Well, it starts at 25,000. Write down what it starts at. Now, after the first year, you would normally multiply it by 70%. It would only be worth 70% of its original value. So somewhere around maybe 21,000, 19,000. That's after the first year. Take that amount after the first year, and again it keeps depreciating the next year, goes down again the next year because it's per year. And it's the same story. You keep getting the 0.7, the 0.7 every single year. You lose 30%, which means you're left with 0.7. So it's the same pattern. It's the same pattern. You're noticing. Instead of writing out, we're going to do this. So you're writing a little equation to tell people about how this situation fits an exponential function. Okay. Same kind of little questions. How about S for sales? S for sales. That's a good letter. How about sales? S for sales. Start with 2,200. Now, in the bracket, what do I put?
excuse this interruption. Can I vote attendance holders main office, please? It's all attendance holders main office. Thank you.
Remember, you always start with 100%. Always start with 100%. So what goes in the bracket? You're going to increase. So increase is a word that means add. So basically you're going to do 100. There you go. It's that easy. You figure out the factor that's going to cause this to increase, and you basically put a little t as an exponent. That's where we are in our story so far. Right? Who can give me this equation? I'm going to leave it mostly blank where it matters. Remember, you start at 100%. What goes in the bracket? A while ago, we started at 50%, had to add 100, and we're at 150. This time, we have to add another 100. Haley, yeah? Go ahead, just try it. 2? Yeah, it's 2. This one's, remember, we start at 100, pick up an extra 2. So that's 300%. So this would be 3. How about this one, though? You have a bad year with your iPod sales. Remember, you start at 100. We're losing 35. 100 minus 35 is 65%. But if you write that, you got to use a decimal. For that easy. Okay, so far so good. Simple little equation with a couple things to find. And we notice the consistency with some variable here, t. Same thing, the t as an exponent. Next part of the lesson, though, changes it a bit. So we're going to add to this. This next part of the lesson adds. Okay? Okay, so, group of zombies. And as you know, zombies come quickly, so it actually follows exponential growth. Just like the graph looks like, it looks like an exponential graph. So let's see what we can do here. How about W for the amount of walkers? Okay. How many walkers are we starting with? 20. Well, how do you know that?
It's right in the middle.
Exactly, it's right here. So you have to look at the graph at time 0. Okay, here's 20. We're about to get into something a little new. So you've been getting it so far, a little bit of an edit, a little bit of an extra thing to check here. Here we go. Okay. This is a situation where we've got doubling. Right here. So if we're at 20, right here, how many zombies do we have when we double 20? 40, right? That's pretty obvious. So where's 40? It's right here. After getting 40 zombies, that'll double again. And doubling that gets you to 80. So now look at the graph. How long does it take to double? How long does it take to have the doubling occur? Here it took from 0 to 4 minutes, and then it took from 4 to 8 minutes. You double 80 to get up to 160. Pretty obvious it takes 4 minutes. 4 minutes, Matt? Brandon? Agreed? Okay, this is the difference now. It's a doubling question. When you double, you put a 2 there for doubling, which means growth by 2. And you're used to, and you're probably going to think, all I need to do now is put a t here, and I'm done. Because that's what we've been doing. It's not what you do though. We're not quite doing that. Here's the key thing. What you put up here is the following. It's always t, but it gets divided by something. In all the other examples, it was divided by 1. What's t divided by 1? T. This one here, it takes 4 minutes for the doubling to happen. Okay, these spaces are all 4 minutes. For the doubling to occur, you need to divide this by 4. You're going to start with 20, and you're only going to double every 4 minutes. So you need to divide by 4. That's how you update the formula. Same as this one if you had wage. So we'll go W for wage. It's $10 to start. It's going to triple. So the tripling is the multiplication factor we need. We know we need a t. But how often does it take to triple? It takes 2 years. So t over 2. Okay. Earlier, I'll just rewind for a sec. Look at all the questions the way they were worded. Your allowance doubles each year. Each year implies 1. We were dividing t by 1. Each year, 1. We were dividing t by 1. Do we have to divide t by 1? Doesn't change it. So we were actually dividing all along. But we don't need to because divide by 1 doesn't change it. Okay, so this one. This is very real figures, by the way. This is true that about 1950 we were 2.5 billion. Now we're pushing 7, 8, I think. But back in 1987 it was 5. How do you do this one? Okay, I'm going to go with P. P's like population. Okay, watch how you do this. What was the original start point? Well, the original start point was a population of 2.5 billion. So I'm going to use units of billion, and I'm just going to write 2.5. I'm not going to bother writing 2500000. I'll just use units of a billion and make the equation easier. Okay? We look at 2.5 billion. We get over to 5 billion. What happened to the population? Doubled.
37 years.
It doubled times 2. That's doubling. We looked at doubling. We folded paper and got to the moon by doubling with exponentials. So we're sure our growth factor or our multiplication factor should double. You have to see that in the word problem. You have to read through the English and see that. Okay? Okay, so always we need t up here. But now the question is, what do we divide t by? What has to get divided by t? Because how long did it take to double? It took 37 years. Exactly. So you do 1987 minus 1950. That's 37 years. You need a 37 there. And you're done. Okay? Okay, hypothetical question. All right, Emily Harrison. It starts in 1950, okay? So if I come up to the year 2000, that's 50 years. So you'd put t as 50. Okay? So at the year 2000, T is 50. So what's T's value at 2020? In the year 2020.
What was it? 70.
So in 1950, T is 0. At the year 2000, T is 50. In the year 2020, 70. So if I asked you, the next question I'll ask you in the worksheet will ask you, and in the year 2020, what's the population? You'll put 70 in there, divide it by 37, 2 to this, whatever that is, and multiply by 2.5, and you can get answers out of these. You can use the equations to get answers. Okay? Thanks. Okay, here's another one. Sharks are dying off due to Sharknadoes. So let's use S for sharks. How many sharks did we start with? We started with 2,500. Okay, so far so good. Right here it says 3 years ago. That 3 years ago, that's what you're going to divide by, because that's when the change is happening. It's sort of like, how long does it take for a change to happen? To go from something old in the past to something new. So the old thing is 2,500 killers. The new thing is there's 1,945 killers. Now the question is, what goes in here? Who has smiters? What has to go in there, guys? This is a decay question. It's definitely going down because it starts at 2,500. So it's some kind of decimal number or a fraction less than 1. Pretty easy. You use these two numbers. Okay, you can think of this as the old number. This one's the new number. And the formula is like old, excuse me, the formula is new over old. So let's just update it. New over old would mean the following. We put 1945 over 2,500. Now anything missing? Just take T out here, because you always need a time variable. Okay, so all these equations have T. That's like your X value. And then you come up with your Y value. I chose S for sharks, Sharknadoes, yeah.
So do they use this to predict stuff in the future then?
Absolutely. Oh, yeah. Yeah. Exactly what exponentials. All equations are meant for that, yeah. All, not just exponentials, all of them. Let's predict the future cost of a movie ticket here. So about cost, current cost is $12.50. Inflation, what's that? Gets bigger, like a balloon inflating, right? Where do we start? We start at 100%. So really we're now at 100 plus 2.9, 102.9%. But we don't want to write percent in here. We just have to convert it. 1.029. Okay? Now, careful. We put a T here. But what goes down there? What do we divide it by? Anyone have a guess? Rebecca?
So we're not divided by anything, isn't inflation anything?
I'll edit the question. A Cineplex movie ticket costs $12.50 right now in the year 2013. In the year 2020, so does that help?
Yes.
So what that should help with is, because it's currently 2013,
Then 7.
it's 7 years. So 7 this year. You're making equations. You're just making equations, and the worksheet you're going to do is going to get you to do that, and then solve them. Actually pick the time values. Maybe you want to know when you're about 40 years old, you have to put the right time in there to solve this, and you can figure out the cost. Okay? When you're 40 years old, you're currently 14. Sorry, you're about 15, 16. So you want to add, about 20-some years, put the right t value. Wow. We have to write down the general formula. Then I'll give you the worksheet. There's the general formula. It's right there. The general formula is always something new depends on the initial value, a multiplication factor, time, and n. And we want to update those. So let me do that for you. Okay, tomorrow we'll do half-life, and it's a work period. Half-life's the last thing on the sheet. Okay, help me out. I'm going to call around the room. Brittany, where does initial amount go? No. Yeah. Okay. Emily Lessel, where does time go? Yeah, T for time. Awesome. Andy, where does final amount go? The final amount. Yeah. Sophia, where's the multiplication factor go? Is that n or b? B. Every time we had a number that between 0 and 1, we were decaying. We were losing from the original. Every time we had a number greater than 1, we were growing. So that leaves amount of time to go here. It's the amount of time for that multiplication factor to occur. Okay? So that finishes the core learning of the lesson. And now you want to be able to read word problems on this sheet here and try these. But take it slow. There's only about 20 minutes. Try a few. We have all day tomorrow to do this. Okay? And effectively, we're sort of at the end of the unit. I think we'll do one more lesson on Monday, and I'm picturing review Tuesday and test Wednesday. That's what I'm kind of picturing. I might push that to Thursday. I don't know yet, but okay. I don't know yet. I have no idea until I see how you guys do this. So let's do a good job. It changes things. If you don't, I have to adapt. Okay? So again, the sheet's for tomorrow, but we don't do every question. I'll show you which one to use, and you can circle.